Hello everyone, welcome back to the MOOCs course on Advanced Analytical Techniques. We are now going to start the fourth lecture of the second week of this MOOCs course. In the previous few lectures, we have completed the emission and absorption spectroscopy. In the previous few lectures, we have completed about the absorption spectroscopy, its instrumentation, working principle, and the different components that are being used in atomic absorption spectroscopy. In addition, we have also discussed about the various types of interferences that are quite common while doing analysis using AAS. And we have also discussed few ways to minimize or prevent those interferences. Then, in the previous lecture, we have started the atomic emission spectroscopy, and we learned that how an atomic emission spectroscopy is different from atomic absorption spectroscopy because both are based on different types of spectrums. AAS is based on absorption spectrum while our AES is based on emission spectrum. Further, in terms of their instrumentation, the only and the main difference between these two techniques is the light source, which is required in AAS but not required in the AES technique. Today, we'll discuss about the different components of this atomic emission spectroscopy. I have already listed the components of AES in the previous lecture. The components are the nebulizer, the excitation source or the atomizer, monochromators, detector and amplifier. We do not need a light source, as you all are aware that a light source is not needed in AES. So let us begin our lecture with the nebulizer, whose purpose is to convert the sample, the dilute sample, into an aerosol. Now there are three types of nebulizers which are quite common in AES. Even some of these nebulizers can be used with our atomic absorption spectroscopy. For example, the nebulizer that I have explained in AAS, it was based on the pressure difference. I told you that there is a tube and then there is a small opening. The nebulizer creates a negative pressure this side, which means that the pressure inside this vessel is very high, which pushes the sample with very high force, resulting into an aerosol that immediately enters either into the flame for direct aspiration or into a graphite furnace if we are using an electrothermal atomizer. The same nebulizer which is being used in AES, it is utilized in AES as well, and they are called as pneumatic or jet nebulizers. In addition to these pressure based pneumatic or jet nebulizers, we still have a choice for two more types of nebulizers called as the ultrasonic nebulizers, which are based on ultrasonic waves, and we have another type called as the electrothermal nebulizers. Each and every nebulizer has its own merits and demerits depending upon the type of analysis and the facilities available, as well as the capital cost with the industry, and as well as the capital cost available in the industry, as well as the research institution. We may select different types of nebulizers. Let us discuss this pneumatic or jet nebulizers. These nebulizers are pressure based nebulizers, and they utilizes the concepts of Venturi. They utilizes the Venturi principle, which says that if a fluid is flowing in a tube, that fluid may be a gas or a liquid. If it is flowing in a tube and if the diameter of the tube is decreasing at some point, for example, this at this point you can see it is, as you can see at this point, the diameter is quite constricted or lower as compared to the other parts like these two parts. So when the diameter is low, the velocity of the fuel at this point, the velocity is very high, and if the velocity is high, the pressure here is low. This low pressure, while in this side we have a high pressure, the high pressure pushes the liquid or the gas towards the low pressure with very high force, and in this way a jet or a spray of sample is formed, and in this case we compress air because the size here is this, because here it is very small orifice which works on Venturi principle. So when a large volume of air is compressed through at this particular point through a very small orifice or through a very small hole, it immediately expands with very high force, and then the sample which is stored here, it mixed with the sample and converts it into smaller droplets to form a uniform aerosol. So when large volume of air is compressed through this small orifice or a small hole, it it then expand with a very high force, and then it mixed with the liquid reservoir, the sample placed over here, and convert this sample into small droplets evenly distributed into this air, forming a very uniform aerosol, from very fine mist of aerosol. Very fine mist or an aerosol is formed. So this aerosol, which is having very uniform sizes droplets, is then entered into the atomizers. We'll discuss about the types of atomizers in later slides of this lecture. Then the second type of nebulizers are the ultrasonic nebulizers. As the name is reflecting, these ultrasonic nebulizers, they works on the principle of piezoelectric effect. There is a piezoelectric crystal placed in the middle of these nebulizers. Upon receiving electrical signal, this piezoelectric crystal converts start vibrating at very high speed. The frequency of this crystal is around 0.5 to 3 megahertz, which is very high frequency. 3 megahertz means 3 into 10 raised to the power 6 cycles per second. So at this high frequency, this creates a force that creates an impact on the liquid sample while air is coming from the top. With the impact created by the vibrations of this piezoelectric crystal at very high frequency, this sample is converted into fine droplets, and these droplets are mixed with air, ultimately forming an aerosol. So these ultrasonic nebulizers, they utilizes the principle of piezoelectricity, where a piezoelectric crystal, upon receiving electric current, start vibrating at very high frequency, and then the impact of that crystal causes this liquid sample into small droplets of uniform size, which are then mixed with air to form a mist or an aerosol. These type of ultrasonic nebulizers are very common with inductively coupled plasma technique, which is inductively coupled plasma is a type of atomizer that is being widely used in AES. So these nebulizers are connected and specifically used with ICP. So the vibration of this crystal, because of this high frequency, creates very high acoustic energy per unit area. Means they create very high energy over a very small area, thereby creating a huge impact, forming small and uniform droplets of the sample. Then comes the electrothermal nebulizers. These electrothermal nebulizers works on the principle of electricity, and they convert that electrical energy into thermal energy. These electrothermal nebulizers works on the principle of electrical energy to heat or thermal energy. They receive signal in the form of electrical voltage, and then they convert it into heat, thereby converting the sample into vaporized form. So in this chamber you can see that we have a heater powered, an electric power heater placed over here. Once it receives an electrical signal, it creates heat and through these rods, and it immediately vaporizes the sample. The sample is injected from the top and placed over here, while this graphite electrodes receives an electrical signal, and at which creates very high temperature, at high temperature which creates very high temperature, resulting into the vaporization of the sample. The time At the time this sample converts into vapor, we passed a blast of argon gas we pass a blast of argon gas that immediately mix with the vaporized sample and converts it into a very uniform aerosol. As you can see that a liquid sample is heated electrically. So electrical signal is required. We have electrodes placed in this nebulizer that creates high voltage and resulting into a heating effect which causes vaporization of the sample, and the moment sample is vaporized, sample forms vapors and inert gas is entered from the bottom which mix with the vaporized sample converting it into an aerosol. The main advantage of these nebulizers over the previous few nebulizers like the pneumatic or jet nebulizers or even our ultrasonic nebulizers is that these techniques completely vaporize the sample, giving very high sensitivity. Means if we have a trace amount of sample available, then even then these nebulizers are very efficient because the loss of sample is very low in this particular case, especially if we are working on some precious metals, for example gold, platinum, and we have some traces of these elements present in a sample and we want to analyze that sample. So we it is advisable for such a precious sample that we should go for electrothermal nebulizers because they require very small amount of the sample, because they require very small volumes of the sample and they completely vaporize this sample present in that small volume without any loss of the sample, resulting into high efficiency. And when large number of molecules are formed in and when large number of molecules are present in the aerosol, the chances of their detection with high precision and accuracy would be very high, and therefore for low volume of sample or for precious metals we always prefer the electrothermal nebulizers because of their high efficiency to convert all the sample into vaporized form. Then after the nebulizers we have monochromator, and we have already discussed about these monochromators because the monochromators are the devices that are used to select specific wavelengths while excluding some unwanted wavelength, and they consist of a prism and slits. There are two slits. One is called as entrance slit or entry slit. The other is called an exit slit. It is a type of a box shape arrangement where we have two slits. One is called the entrance slit, which allow only a which allows specific wavelengths to enter. Then we have mirrors over here to reflect, and we either use a prism or we can also use a grating which is like this, which converts these radiations into individual wavelengths. And then there is a mirror again which reflects them back. This mirror is called as focusing mirror, and ultimately some of these radiations are blocked while only selective wavelengths are allowed to pass through this exit slit. So in this way this device basically help us to select the specific wavelength in which we want to carry out the study. Clear? Now one main point with AES is that in AES this monochromator is placed after the atomizers. I am just explaining it here because this is a small device and the purpose is limited to the selection of wavelengths only, while atomizers, especially the atomizers or the excitation source which are used in AES, they have number of functions. For example, they perform desolvation, then they perform vaporization, then dissociation, and finally excitation. So there are multiple purpose of an excitation source or an atomizer in AES. Therefore we'll discuss it in detail after discussing briefly about these monochromators, because this monochromator has a specific function of selecting a wavelength. That's why I am discussing it before our excitation source, although this monochromator is placed after the excitation source because there is no light radiation in an atomic emission spectroscopy before the excitation source. Once the sample entered into the excitation source and it is heated at high energy, the electrons are promoted to higher level and then they return back. When they return, they emit light. Then only these light radiations are emitted, and we need a monochromator which is placed after this excitation source, so that from the emitted light radiations, this monochromator select few desired wavelength while blocked the other. So in AES, we first have a, then we have excitation source or an atomizer, and finally we have monochromator to select specific wavelength that are being emitted when sample is heated in the excitation source, and at the end we have detector placed over here. So this monochromator is a combination of a prism and two slits. Even if we can take atomic grating as well. For ICP plasma technique, sometimes instead of a monochromator, we use a polychromator. As its name is reflecting, a polychromator has the ability to select multiple wavelengths as at a time, because ICP can be used for the analysis of multiple elements. That is the beauty of ICP. That is the main advantage of ICP, that it can use to analyze multiple elements simultaneously, and for such a case we do not need a monochromator, but we need a polychromator. In that we'll discuss in some other lectures. So as it is written, for simultaneous multi-element analysis, polychromators are used. So this is a schematic diagram of a monochromator, where we have an entrance slit. The light is coming, this light is coming from the, so this white light is coming from the excitation source, and it is a emitted light which is emitted when electrons of the sample after excitation returns back to their ground state. Emitted light, then it passes through a slit. Here this entrance slit also excludes some light radiation and allows some of them, and then it falls on a concave mirror which directs it towards a grating. So the light radiation, some of the light radiations are excluded by the entrance slit, they falls on the concave mirror and further reflected back to the grating. Then and these grating allows this grating convert this light into individual wavelengths, or disperse this light into individual wavelengths. This passes through culminating lens, and if we have a polychromator, we have a prism. We again use a prism that further distribute these light radiations into their further derivatives. For example, here you can see there are, this white light has been divided into 4 or 5 colors. Then these 4 or 5 colors further pass through this lens and ultimately falls on the prism, which converted it into more of its radiations. So here you can see more colors. And then finally we have a charge coupled device as a detector, because in case of atomic emission spectroscopy we can have photomultiplier tube as a detector, but if we are dealing with polychromators and we are doing a multi-element analysis, we have to use a detector that can detect multiple elements at a time. This device has the ability, this detector charge coupled devices has the ability to detect multiple elements at a time, and for polychromators these CCD devices are used. And when we are using a polychromator, this is the structure of a polychromator, where we use a grating as well as a prism to the grating first of all convert this white light into 4 or 5 individual colors, and these colors are further divided into or further converted into their respective more number of wavelengths that represents each and every element that corresponds to the different elements present in the sample, and these radiations when fall on the CCD device, the charge coupled device, it detects all the elements simultaneously. So this is the beauty of a polychromator, and this polychromator is connected with a CCD device, and this whole assembly is used with an ICP-AES, means the inductively coupled plasma atomic emission spectroscopy. In the later part of this unit, I will be focusing on the inductively coupled plasma, where there I'll explain you about the plasma, how the plasma is formed, what is the temperature range of this plasma, and how it is useful over the other excitation techniques that we'll discuss later. So this is all about the polychromators. Then comes to the excitation sources, which is the most important component of an atomic emission spectroscopy. Although in case of AAS, only limited number of atomizers available, the common atomizers in AAS are flame atomizers or graphite furnace atomizers. Flame atomizers are called as direct aspiration, while graphite furnace atomizers works on the electrothermal nebulizer principle. But in case of AES, we have a flexibility, we have a range of excitation sources, right from the beginning with flame excitation, which is similar to our flame atomizers or the direct aspiration technique. We then have an alternating current arc. We also have a DC current arc, alternating current spark. Spark means just for a few microseconds only it is created. It is a momentary, it has been created momentarily and immediately it extinguishes, but in that moment only it creates so much energy that the sample is completely undergo the excitation, desolvation, dissociation, everything. And then we have plasma excitation sources, which are further divided into three different types. The one of the most popular, the inductively coupled plasma technique, the direct plasma technique, and the microwave plasma technique. All these plasma techniques are very, very important because they have very high energy that can transform almost all the metals into their excited state, into their vaporized state, and then their excited state. And out of these three, ICP is the most widely used technique. But before moving on to the plasma techniques, we'll first discuss about these excitation sources. So let us begin our discussion with the flame excitation sources. This flame excitation, as you all know, if we compare the flame excitation or the direct aspiration method with the electric arc or spark or even the plasma technique, they the flame excitation sources have limited energy than the temperature we can achieve in electrothermal process or in case of plasma techniques. Therefore, flame excitation is limited to the metals that can be ionized easily. So we use this flame excitation for metals that can be vaporized as well as excited easily, so that in the limited range of the temperature up to 2000 or 3000 degrees centigrade, we get the excitation of those metals. But for other metals which are high melting point metals, we do not use this flame excitation technique because of its limited energy. Further, this flame excitation is a type of open excitation. Further, this flame excitation is a type of open excitation where we heat the sample openly. Openly means where we heat the sample in presence of air or oxygen gas as an oxidant or even nitrous oxide. So there will always be chances of oxidation, which results into the formation of sometimes which results into the formation of stable metal oxides which do not dissociate, and ultimately the results obtained are not reliable. So flame excitation is always limited to metals that ionizes easily, they are those metals which vaporizes easily and which for which the possibility of oxidation or reaction with oxygen is low. So in this technique, what we need is, because the sample is coming from the nebulizer in the form of an aerosol, now we need fuel. We have options for available, like hydrogen can be used. We can also use acetylene, like in AAS acetylene is very common. Further, we also need oxidant. So tell me what oxidant we can use. We can use oxygen, pure oxygen. We can also use air, and we can also use nitrous oxide over here, any of the oxidant. So generally we prefer either hydrogen or acetylene along with oxygen to produce the flame that ultimately causes the sample to vaporize, dissociates into individual atoms, and then finally excite those atoms. This is a schematic diagram of our flame atomizers or the flame excitation sources, where we have the flame in the middle, while this chamber has two inlet, one for the fuel, other for the oxidant. These two mix together to create a flame just at the open end of this chamber, while sample in the form of aerosol enters through this capillary right at the middle portion of this chamber. The sample ejects out or eluted from this capillary type column from the middle, where we have the flame lighting up, and the flame burns the sample, vaporizes the sample, dissociates it into individual atoms, and finally excite those atoms. These excited atoms have their electrons promoted to their higher level, and when the electrons returns back or de-excite, they release energy, they release light, which is detected by a detector, commonly photomultiplier tube if we are dealing with one element at a time, or a charge coupled device if we are of course working with multiple elements analysis at a time. And be between the detector as well as this excitation source, we also have a monochromator, or sometimes a polychromator. If for multiple analysis we have a polychromator, otherwise for a single analysis we use a monochromator. So when the sample enters through this capillary tube, while we have two inlets for the fuel as well as oxygen gas, they creates a flame with very high temperature. When the sample eluted from that capillary tube, it first of all undergo desolvation, then vaporization. It undergoes desolvation, then vaporization, dissociation, and finally excitation. Although these flame atomizers have limited energy, but they are still low cost and they have simple design. Although they have low energy, but they are still low cost, and they have simple design that can not require a highly trained labor, that cannot require a highly trained personnel for operation of these atomizers. Further, in order to get reliable results, in order to get reproducible results, we always try, the flame should not have a turbulent performance, it should not vibrate, it should not have uh, it should not uh, it should not get affected, or for better performance the flame should be stable and non-turbulent, otherwise the results will not be reproducible. And also the length of the flame as well as its energy should be sufficient to vaporize and excite the sample or present in the sample. If in case we have an impression that the analyte has high melting temperatures, we must avoid using flame atomizers, and we should go for either electrothermal atomizers or the plasma atomizers. Then comes the alternating current spark or AC spark. In a spark, an electrical energy is created for a very short period of time. That is why it is called as a spark. This spark is created between two electrodes momentarily. It remains active for microseconds, which means the time is very small. And since the time is small, the contact between this energy and the sample and this energy is for a very short time. Therefore, the energy should be very high so that in that moment only, in few microseconds only, it should be able to completely vaporize and dissociate as well as excite the sample. And for that, we use an AC spark of 10 to 50 kilovolts, which is a very high voltage. 10 to 50 kilovolts means 10,000 to 50,000 volts. This AC spark, an AC spark is generally created with the help of a capacitor, which is a device to store energy. So what do is we take a capacitor, connect it with two electrodes, and we charge the capacitor first with very high voltage of 10,000 to 50,000, and then in fraction of second we discharge that capacitor and transfer all of its energy into those electrodes to create a very high energy spark for fractions of second that should be sufficient enough to vaporize and excite all the sample. So the capacitor which is used has this capacity 0.005 microfarad, and that capacitor is being charged with such a high voltage, and then that capacitor is allowed to transfer all of its energy, all this charge within fraction of second to the electrode, so that a very high, very high energy spark is created, that has the sufficient energy to transform all the sample into an excited individual atoms, which then creates an emission spectrum. Clear? So the current can be further increased. Sometimes condensers are also used to increase the current, but this is also sufficient voltage which creates a high energy with the help of a capacitor, and this technique is used for a wide range of sample. A number of elements can be analyzed with this technique. Further, there is also an advantage of this technique is that since it creates for a very small period of time, for a short period of time, even high concentrations can be analyzed with this particular technique. Because for high concentration, if the energy is too high and the energy stays for a longer period, then almost all the concentrated sample is converted into vaporized excited form, and there will be large amount of emission of the light, which creates multiple peaks and ultimately results in complication of the spectra. Therefore, we most of the time require dilute sample. But if we have a concentrated sample and it is not possible to further dilute it, then we may go for using AC spark, because it exists for a very short period of time, so even higher concentrations do not affect this particular analysis. These are the advantages of AC spark. Even the small amount of sample is needed for that sample as well. It can be used. It is reproducible. Since the spark is generated for a very short period of time, it can be used for the analysis of low melting materials as well, because sometimes the materials melt very fast, and if this material is melted, we may have different results. So for those samples as well, we can use AC spark. Low melting materials, we have different types of metals, like we have bismuth, we have tin, we also have iridium, mercury. These are the metals which are These are the metals which undergo melting very fast. So for these metals, we use AC spark because here the energy because here the energy exists for a very short period of time. Even concentrated solutions, as I just mentioned, that even concentrated solutions can be analyzed, because concentrated solutions, if heated for longer period of time, they have large number of atoms in excited state. Therefore, for these such solutions we prefer a momentarily available energy which is only passing, and since the energy is for very short period, the chances of interferences are also quite low. And again, very high temperatures can be achieved because we have high voltage of 50,000 and that is transferred into those electrode through a capacitor for a very short period of time. So can you believe at that very high voltage in a small time? So all the energy can be transferred immediately, which creates a very high temperature. Then AC arc. The difference between AC spark and AC arc is that AC spark exists for a very short period of time, while an AC arc can exist for longer periods. These AC arc are used in various applications, even in welding. It has so much energy that it can melt iron rods as well. And in case of AES, we do not have an iron rod, or we do not have a solid sample. We have a sample which is present in liquid form, where we have individual molecules dispersed in liquid, and they are further converted by a nebulizer into an aerosol, which we have to excite only. So these have sufficient amount of energy. Here again, an AC arc or or alternating current arc, an electric discharge between the two electrodes is created, and this electric discharge is used to atomize as well as excite the sample. Means excite means ionize those samples. Here we uses a potential difference of 1 kilovolt, while in the previous case, in case of AC spark, it is 10 volt, 10 kilovolt to 50 kilovolts, which means up to 50,000 volts, while here it is only 1000 volt. Why so much of energy in the AC spark? Because that existed for a very short period of time, therefore we need extra energy, we need more energy. While it AC spark exists for longer period of time, therefore the energy requirement is not very high. We can achieve that energy just by giving 1 kilovolt or 1000 volts. And this AC arc is placed at a distance of 0.5 to 3 mm from the sample. For example, if the sample is coming from the nebulizer over here, it is eluted here in the form of aerosol, we use two electrodes which creates this electric discharge, and the distance between these two is from 0.5 to 0.5 to 3 millimeters, depending upon the type of metals under study. For high melting metal, we keep it more closer at 0.5 millimeters, while with metals having moderate or low melting temperatures, we keep this electric discharge at a distance of 2 to 3 millimeters from the sample. Even non-conducting samples can be analyzed with this technique. If the sample is non-conducting, we mix it with graphite powder to make it conducting. Again, we have minimum interference as we have in case of AC spark, because the energy is very high. Further, there is a possibility that all the sample is being converted, so there will be no loss of the sample. Most of the sample is converted into ionized state, so the results are quite reliable and reproducible. The spark obtained from AC arc is quite stable as well as reproducible. We can get same spark, we can, even the arc is quite stable and reproducible, we can get the same energy number of times. This ACR can be used for concentrated solutions as well, because it has also high energy, and since it is an AC arc, AC arc can only be produced when we have a continuous supply of energy, while for AC spark we need energy momentarily. Therefore, we use a capacitor that transform all the energy stored in the capacitor to this AC spark once at a time, once on, so that the capacitor can transform all the energy stored in it to the AC spark once. While in case of AC arc, it has the discharge should be for a longer period, so we need a continuous supply. While but since it is an AC arc, it is not a DC arc, so there are always, it always occurs in a cyclic fashion. Therefore, we can have these concentrated solutions analyzed as well. Because of its very high energy, the atomization of the aerosol is quite quick. So these atomizers or excitation sources takes very little time or very short time is needed to convert the sample into ionized form. And again, since we have excessive energy, we have high voltage we are using, since we are giving excessive energy and high voltage, the temperatures achieved can be as high as 5000 Kelvin, that are sufficient to excite and ionize most of the elements in the periodic table. The next is our DC arc. A DC arc or the direct current arc is again a continuous discharge of electricity by using a direct current source by using a direct current circuit. If we compare an AC arc and with a DC arc, both have their own advantages and disadvantages. Although both of these although both AC and DC arc require continuous supply of energy, because they have to create the arc or they have to discharge the electricity for longer period, but they have differences as well. Like AC arc uses an alternating source, so sometimes there will be very high energy, then low, so we can use it for concentrated samples as well. But on the other hand, direct current arc have constantly on the other hand, direct current arc have constantly high energy and very high power that are being produced. So if we have a concentrated sample in a DC arc, it will convert all the sample, which again causes very high number of atoms in ionized form, emitting large amount of light, which creates a complicated spectrum. Therefore, for concentrated sample, it is not preferable to use a direct current arc, but it can be used for trace analysis, or it can be used if the sample volume is very low. For trace elements, for example, if in a sample we have some element, some heavy metal at very low concentration of parts per trillion, or it may be 0.01 parts per billion, then in that case, since the concentration is very low, we need and we need to detect such sample. So if we are using an AC arc, then it will not ionize, or it will not convert all the sample into it will not convert all the sample into vaporized and ionized form. And even if we are working with AC spark, the chances for converting all these trace element present into the ionized form, even the chances with AC spark are even lower to convert all these samples into their ionized form. Therefore, for such a dilute sample containing trace quantities of some elements, we always prefer direct current arc or the DC arc. So, and the advantages of this DC arc, it can be used for welding purpose as well, which shows its high energy that even it can melt metal rods while we are dealing. So it can be used for welding purposes, so it has sufficient energy to melt metal rods while we are dealing with liquid samples only. So it has very high energy, even higher than our AC sources, and it has more stable arc. And you can see here this arc between two electrodes, it has very high energy. And further, it has less spatter, means all the sample, most of the sample is getting transformed into vaporized and ionized form, so the chances of diminishing of this arc or lowering of its energy are very low. And above all, it is useful for trace elements. So both AC arc or AC this spark has an advantage that they can be used for samples with very high concentration. For concentrated sample, we can use them, while a DC arc has another advantage that they can be used for trace elements. So with the availability of AC arc or spark and the DC arc, we are able to analyze even highly concentrated sample as well as very dilute sample containing trace amounts of elements. So there is a wide range over which these this machine can operate, from high concentrations to very low concentrations. Then comes to the plasma as an excitation source or ionization source. So before moving on to plasma, I should ask, what is a plasma? Do you know what is a plasma? A plasma is also known as the fourth state of matter. Till then, we have studied only three states: the liquid, the solid, liquid, and gaseous state. But plasma is the fourth state, although there are five states. According to physics, there are five states: solid, liquid, and gas. Three states. Then we have plasma, which is a very high temperature state where we have ionized gas. Ionized gas is present in plasma. So when a gas is heated at very high temperature, so that the gas is ionized, for example, if an inert gas is heated argon at very high temperature, it forms Ar positive and electrons, then this will create a plasma. Then the fifth state is called as Bose-Einstein condensate, which is a very low temperature state. So in terms of lower to higher temperature, I should say Bose-Einstein condensate is at the lowest temperature, so it is the first state. Then we have solid state, then liquid, then on further increasing the temperature, we have gaseous state, and finally at very high temperature, where even the gas form and where even the gas is ionized, that state is called as the plasma state. And for creating a plasma, we require two things. What are those things? First is the heat source that provides thermal energy, and second is the gas. You cannot create a plasma in vacuum where nothing is present. Even if you give very amount of large amount of heat, or if you pass very high voltage, nothing will be created. Plasma is created from gas. When the gas is heated at very high temperature, it undergoes ionization to give cations of that gas along with electrons. Then it creates a plasma. So for plasma, we need first of all gas as well as a heating source that converts the gas into a ionized gas. Now there are three ways of creating a plasma. One is by using magnetic field. That's why it is called as inductively coupled plasma. Here we used the concept of induction. We use magnetic field. In this case, we use direct current DC source for creating a plasma, and in this case we use a microwave, which is a type of an electromagnetic radiation, to create a plasma from a gas. And a plasma can go very easily up to 8000 degree Kelvin or even higher. We can achieve 10,000 degree Kelvin temperature in plasma, while with electric arc or discharge we can go up to 5000 Kelvin. So this is the beauty of plasma, that we can achieve exemplary high temperatures. As I said, an electrically conducting gas mixture is called a plasma. It contains ionized gas molecules, means cations as well as electrons, and they are only formed when gas is heated either by electric discharge or by giving direct heat at very high temperature. Then there are three different plasma sources: inductively coupled plasma, the direct current plasma, and microwave induced plasma. And they have the capacity to achieve temperatures of over 10,000 kelvins. Out of these three techniques, inductively coupled plasma is the most interesting and most widely used technique. Now, advantages of using a plasma in atomic emission spectroscopy: it is a rapid technique because it offers very high temperature, very high thermal energy, So it immediately transforms sample into vaporized and ionized form. So it saves time. It is very quick. It can be used for multiple analysis at a time, some multiple analysis simultaneously. Even some non-metals like chlorine, bromine, and even sulfur can be determined by this technique. And this technique can be used for very high as well as low concentrations. Can be used for even concentrated as well as dilute samples. Of course, there are certain disadvantages of plasma as well. Everything has its own pros and cons, merits and demerits. Just like that, this plasma technique has its own demerits. First of all, if we are doing a multiple analysis, there will be number of peaks. Some of them are very close to each other, creating ambiguity or complication in the analysis. The second demerit is that a plasma, because of the plasma source, the AES becomes very expensive. If an AES is using a plasma as excitation source, the cost is very high as compared to its counterparts like electrothermal excitation sources or the flame excitation sources. Further, because very high temperature up to 10,000 degree Kelvin are achieved, we need highly trained person to operate this machine. We cannot allow anyone or everyone to use this technique. Therefore, we need extremely trained personnel for this. And since the machine is costly, even if some component is damaged, especially the high resolution and optical components, they are highly costly. If damaged, they require huge sum of money for replacement or repair. With this, we have covered the different components of AES. Now in the next lecture, we'll talk about these three plasma techniques, how we can create a plasma by using microwave or direct current, and then we'll discuss about inductively coupled plasma in the next lecture. Till then, stay blessed. Thank you very much.